Every headline about battery breakthroughs eventually hits a wall of physical reality. We hear promises of faster charging or longer range, but these claims often lack the engineering backbone required for actual manufacturing. Today we look at a specific material science story that solves the scaling problem where most others fail. A new magnesium-tin alloy has achieved a stability metric that changes everything about how we build batteries. The headline number is 1,300 hours of stable cycling life. That single figure represents a 40-fold improvement over previous attempts and, more importantly, it clears the specific engineering hurdle that keeps this technology stuck in laboratories. For decades, magnesium batteries have been the dream for high-density storage without expensive metals like lithium or cobalt. The problem has always been the anode. When you try to use pure magnesium metal as the energy source inside a battery, it does not play nice with its surroundings. It degrades rapidly at room temperature and forms corrosive layers that kill the cell in hours rather than years. Tohoku University researchers engineered around this failure by creating a specific alloy compound known as Mg2-sin. This is not just mixing two metals together, it is an architectural change to how ions move through the material. The breakthrough lies in how this magnesium-tin combination regulates ion transport during charging and discharging cycles. By doing so, it suppresses the formation of dendrites, tiny spikes that can short-circuit a battery, and stabilizes the solid electrolyte interface layer that protects the anode surface. Think of the traditional graphite anode used in your phone or laptop as a porous sponge where lithium ions fit into empty spaces without changing the shape too much. Magnesium behaves differently. It wants to alloy with other materials, expanding and contracting significantly during operation. Without a buffer structure like this engineered alloy, that volume expansion causes mechanical fracture every time you charge the battery. The Mg2-sin lattice acts as a shock absorber for these massive physical changes, allowing the material to expand and contract without crumbling apart after just a few cycles. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The result of this structural stability is the 1,300-hour metric we started with. This number validates that the suppression of dendrite formation works effectively at room temperature. In previous magnesium systems, you often had to heat the battery up significantly to prevent corrosion or force ions through the interface. That requirement made mass manufacturing impossible for consumer devices which must operate in a wide range of ambient temperatures without external heating. By solving this interfacial degradation issue, the alloy enables reversible reactions that were previously thought too unstable for practical use. This shift from high-temperature operation to room temperature stability is what unlocks commercial viability. It means we can finally consider magnesium batteries not as laboratory curiosities, but as potential replacements for current lithium-ion technology in large-scale applications. The 40-fold increase in cycling durability demonstrates that the alloy's lattice structure effectively buffers the massive volume expansion during plating and stripping processes. This mechanical resilience is a critical architectural prerequisite for scaling solid-state cells without them fracturing under physical stress over time. However, we must look at this through an engineering lens to understand what comes next. While the chemistry works in the lab, the path from a single test cell to millions of manufactured units involves complex material synthesis challenges. The success of this alloy relies on precise control of interfacial reactions that are difficult to replicate consistently across large batches. This is where the manufacturing story diverges sharply from our current lithium-ion supply chain. Today, we have a mature, standardized production process for graphite anodes. Factories know exactly how to coat them, dry them, and pack them with high yield rates and low costs per kilowatt hour. The Mg2-sin alloy introduces new variables into that equation. Creating the specific crystal structure required for this stability demands tighter tolerances during synthesis than currently exist in standard battery assembly lines. We do not yet have data on cost per kilowatt-hour comparisons or the initial yield rates when attempting to mass-produce these complex alloys at scale. There is also a fundamental shift in how we think about electrolytes and safety. Unlike traditional graphite anodes, which rely on intercalation and carry risks of lithium plating if charged too quickly, this magnesium-tin system enables reversible alloying reactions that eliminate the need for some of the expensive or corrosive components found in current high-energy systems. This fundamentally shifts the cost-benefit analysis for industrial battery pack assembly. If we can solve the synthesis complexity, the potential for cheaper, safer, and denser batteries becomes a reality rather than just a theoretical possibility. The research focuses on solid-state configurations where these reactions occur most reliably. This means the transition to liquid electrolyte systems, which are common in current consumer electronics, remains an unproven step that must be taken next. Engineers will need to determine if this stability holds when exposed to different chemical environments outside of controlled solid-state testing. The 40-fold boost is a compelling engineering milestone, but it represents only the first layer of validation required before we see these batteries on store shelves or in electric vehicles. The core takeaway here is that battery technology has not been stagnant. It has simply been waiting for the right physical solution to scale. We often confuse software optimization with hardware capability, thinking that better code can fix a material limitation. But this story proves otherwise. The constraint was never about how we manage power in an app or optimize charging algorithms. It was always about whether the materials could survive thousands of cycles without disintegrating under their own physical forces. With 1,300 hours of stability, researchers have crossed that threshold for magnesium-tin alloys. They have shown that by engineering specific lattice structures to handle volume expansion and suppress dendrite growth, we can create a battery chemistry that is both high density and durable at room temperature. The challenge now shifts from the laboratory bench to the factory floor, where consistency becomes king. If manufacturers can master the synthesis of this alloy with the same precision they apply to graphite today, we could see a new generation of storage technology that bypasses many of the cost and safety bottlenecks limiting current energy density. This is what physical layer engineering looks like when it moves from theory to practice. It is not about faster chips or smarter software. It is about building materials that can withstand the brutal reality of repeated charge cycles without failing. The path forward requires bridging the gap between laboratory-scale stability and industrial manufacturing consistency, but the direction has finally been cleared. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.